This time we're going to be putting some numbers into the model of the inverting op-amp amplifier that we investigated in the last video. Right, just a reminder that when we combine all of these sources, we have to combine their powers, the squares of the noise voltages, and add them up. And then our final noise voltage is the square root of the sum of the squares of the individual noise voltages. And we have to do that whenever we're dealing with independent noise sources. So, back to the circuit. We have 5 noise sources. N1 was the noise due to this equivalent input current here. And as we saw before, that has no effect on the output noise at all. Contribution is 0. N2 is the noise due to this current here. And if you put the numbers in for a TL071 based inverting amplifier with a source resistance R1 of 10k and a feedback resistance R2 of 100k, then what we get for the contribution of this noise current here is 1 times 10 to the minus 18 volts squared per hertz. Now that, just comparing it with the other contributions here, is 3 orders of magnitude below any of the other contributions of noise. Therefore, it is safe to neglect it. N4 is the contribution of the noise due to the feedback resistor here. It's this term here, ET2. And as you see, that contributes only 1/10 of the noise from either of the other 2 sources, and in terms of noise, that makes it negligible as well. The only 2 noise sources here which contribute significantly to the output noise are this one, the equivalent input noise of the op-amp, which contributes nearly 4 times 10 to the minus 14 volts squared per hertz. That's the biggest single contribution. And the input source resistor here, which contributes 1.6 times 10 to the minus 14 volts squared per hertz to the final noise power. Add up those 2 contributions, take the square root, and it gives us a total expected output noise of this amplifier of 238 nanovolts per root hertz. One quick word though, we haven't included in that calculation the effect of the larger than expected noise at low frequencies, this 1/f noise here. If we wanted to include that in our calculation, we'd have to take the contribution from the equivalent input noise here and split it up into 2 parts. One part from 10 Hz to 10 kHz, we know the total input equivalent noise for that frequency range, and one part from 10 kHz up to the maximum frequency that we're interested in, and for that noise contribution we can assume that the noise is white. We can use the insights gained from that analysis to simplify the analysis of more complicated circuits. For example, this differential amplifier here has a total of 7 noise sources contributing to the noise in its output. 1 for each of the resistors, 2 input noise currents for the op-amp, and 1 input noise voltage for the op-amp. However, our experience would suggest that this noise due to this feedback resistor here is negligible compared to the noise coming from the input resistor R1. And the same is true for this pair of resistors as well here. This contribution of ET3 is much more significant than the contribution from ET4. We know that for this op-amp, the effects of the input currents are almost negligible, so it's only these 2 noise sources, ET1 and ET3, and En here, the equivalent input noise of the op-amp, that we need to consider. Just those. And if we only consider those, then this is the output we get for a different op-amp, one with a rather lower noise figure than the TL071. The MCP6291 has an equivalent input noise voltage density of 8.7 nanovolts per root hertz and the input noise current density is a tiny 3 femtoamps per root hertz. It's really not going to be an issue in any circuit that we're going to build with sensible values of resistors around it. That would suggest that for this differential amplifier, we could simplify the analysis quite a bit, just consider these sources and end up with a total of 101 microvolts RMS of noise in a 20 kilohertz bandwidth. That's the end of this one. Next time, just a few hints and tips about how to simulate with noise sources in the simulator.